low pressure. I don't have to update it every day.
Okay, good morning. Welcome to the beginning of week 2. I just now posted the course materials that I'm going to be using this morning. I'm sorry for being late with that. Actually, all of the course materials are in the files area on Canvas, so you can, look ahead at what's going to be coming up in future weeks. I wanted to start things off. Well, let me first start things off by asking if anyone has any questions from last week or anything about the homework. Alrighty, so the first homework was just intended for you to kind of get your feet wet with Python, get a little bit of experience using Jupyter. Jupyter is a tool that people like to use for interactive data analysis kinds of tasks. It's a little bit like the statistical equivalent of the Excel spreadsheet. You can write programs using Jupyter, but it's really more intended for interactive kind of use. You'll be better off for the remaining work that we're going to be doing using some kind of better integrated development environment like Spider or PyCharm. But having some exposure to Jupyter is useful. All right, so we've taken a look at the fundamental data types, arithmetic, logic, decisions, variables, etc., etc. We didn't quite make it through last week's stuff, and so I need to talk about modules. A module in Python is simply a single source code file that presumably contains things like objects or functions or classes that are related to one another in some way. And you can import a module if you want to use the facilities that are described in that module. Now, in Python, when you import a module, it is as though you went out and you found that file, that source code file for the module, and you copied and pasted that in place of your import statement. So in effect, it's like, you've just dramatically expanded your own source code by whatever the contents of that imported module is. One very common one that everybody uses who's doing anything interesting is the math module that contains all the usual mathematical functions, as well as some constants. For example, here I am in my Python shell, my interactive shell. If I ask for the e to the 1 power, I hit F1 again. Okay, if I ask for e to the 1 power, I get told, nope, exp is not defined. So what I can do then is to import the math module. Import math. And now I can use any of the facilities available in that math module by typing the name of the module and then the name of the facility that I want, in this case e to the x. So math.exp e to the 1 power gives me the value of e, to the precision that Python is able to store, of course. Many modules have much longer names than just math. So a common thing to do is to provide a 1 or 2 letter abbreviation for the module name when you do your import. Here I'm saying import math as m. Import math as m. Now I can use m as an abbreviation instead of having to spell out math, and I can say m.exp2, let's say, and there's e squared. You can also, by using from, import individual facilities from a module rather than importing the entire module. So let's suppose that I didn't care about sines and cosines and logs and various other things, and all I wanted from the math module was just the e to the x function, I can say from math import exp. And now that exp function is put into the so-called global namespace, the top level of my Python shell. And now I don't need any prefix. I don't need to see math.exp or m.exp. I can just directly say exp1 to get the value of e to the first power. You can, and this is risky to do, if you decide that you want to use every single thing that's available in the math library, and you want all of it to be available at the top level, you can say from math import everything. Okay, star means everything, every single name, every single function, every single constant, every single class, on and on, from that math library will be imported into your top level environment. All right, so if I do that, I can say from math import star, and now I can say things like e to the square root of the sine of pi. Now pi is, let me show you that first, I guess. Pi is an object that's part of the math library, and it contains the value of pi out to the precision that Python is able to store. And so if I ask for the sine of pi, if your trig is up to speed, you'll know that that should be 0. No, minus. Yeah, 0. Yeah, sine of pi is 0. See, I did physics for years, and I have all of this stuff permanently emblazoned in my brain cells. And of course, now I forgot. So the sine of pi is 0. But this is as close to 0 as Python is able to compute. All right, when I invoke the sine function on the pi object, I get something that's really close to 0, but it's not exactly 0. If I now ask for the square root of that thing, I get something that's slightly less close to 0. And if I ask for e to the square root of the sine of pi, that should be exactly 1, because anything to the 0 power, well, any positive value to the 0 powers should be 1. But I have this floating point round-off error that's preventing it from being exactly equal to 1. All right. So two things here. First of all, you can import modules to provide additional services for yourself. And beware that anytime you're doing floating point calculations, you're going to be carrying around this round-off error. You just have to be aware that error is going to get worse and worse and worse and worse the more floating point calculations you do. So far, so good? All right. Now, one final warning I want to give you about doing from math import star is, do you know the names of all of the functions, all of the objects, all of the classes that are in that math library? No. And the way Python works is, suppose you had already defined for yourself a function. Did I show you one trivial example of how to define a function? Did I define foo the other day? All right, so let me define a function that returns to you the cost of a tan. All right, you're going to get a tanning session at a salon, so we're going to define a function here that tells you the price of a tan. Unfortunately, there's also an arctangent function named atan in the math library. And so if you have got your a tan function defined that tells you the price of a tanning session, and you import star from math, your a tan function gets replaced by the math library's arctangent function. Silently. There's no complaint from Python about that. So as a general thing, it's considered reasonable to import individual facilities that you want, individual functions or objects or classes from a library, but it's generally best to avoid doing an import star, because you probably can't keep track in your head of what all the stuff is that's going to overwrite things that you already have. Make sense? Okay. All right, well, the last thing we're going to take a look at here in this first part, this week 1 stuff, is how to read from and write to a text file. In particular, we're taking a look at copying a text file in this case. In Python, this function called open is built in, so you don't need to import any modules in order to use open. Let me start my editor running. File, new file. And let me create, let me save this file, save as. Okay, well, I really want to be in my DFP-B3 2020 directory. So let me restart my idle. All right, so I'm going to exit from idle. And back in my Anaconda shell, I want to cd into DFP-B3 2020. Hey. Maybe it's underscore B3 2020. Yeah, there we go. Okay. All right, so here I only have this example1.py file that I created last week, which just has a couple of variables and some print statements in it. Let me run idle from here. And now, when I say that I want to create a new file, new file, and save this, file, save as, I am now in that DFP-B3 2020 directory where our class's stuff is located. This one's going to be called mycopy.py. Okay. So, in order to copy a file, the first thing I have to do is to open that file to read text from the file. Okay, we're not dealing with binary data here, we're dealing with text data. So, to the open function, the first argument that you specify is the directory path and the actual file name of the file that you want to open to read data from. And what I've got here is just a representation. If on your system you did actually have a top-level directory named dir1, which in turn contained a subdirectory named dir2, which in turn contained this file in.txt, you could use that path name to access that file. We want to read text from this file, and we're going to assume that the files we're dealing with are probably ASCII files. So the third argument we specify to open is the character set in which the input is encoded. And because ASCII is a direct subset of the UTF-8 Unicode character set, we can use UTF-8 as our encoding. Okay, there are lots of other arguments that the open function can take as well, but these are the three that you need to worry about the most. Where the file is and what its name is, whether you want to read from the file or write to the file, we're reading from this input file, and what the character set is that that file is encoded in. All right, so I'm going to put that in here. Let me say this is file my copy.py, and I'm going to say fin for file input. It's not a very clever name. Open. Now I know that I only actually have one text file in this directory, which is the, where'd it go? I can't find it. Which is this ex1.py file. Okay, ex1.py is the only text file that I currently have in this directory. So for illustration purposes, let me open that ex1.py file. Since that file is in the current directory where my idle environment is, I don't have to specify a hierarchy of directories to get to it. I know that it's right there. Now I can, if I want, I can say /users /jostland /dfpb3 2020 / I can do that, but I don't need to, since that's the directory that I'm currently in. Actually, there's one other thing that I should say here that I didn't. Notice that I'm using the / here as in my directory paths. Python uses the Unix/Linux convention for identifying file path names, which is the / rather than the \. Now, you can use the / instead. DFPB3 2020. You can use the / instead. The problem with the / is, do you remember we have things like \n, which is the new line character, and we have \t, which is the horizontal tab character? Well, that means that if you want to use / in your file directory path names, you have to double the \ all the time. So that the first / tells Python that the second / should be treated as a literal character. And everybody always forgets to double the \'s, so I recommend just following the Unix/Linux convention that Python is expecting anyway, and use the /, and it will work just fine. Make sense? All right, so I'm going to get rid of that stuff I don't need. Well, I might as well leave it in there since it doesn't hurt anything. Now, I'm going to read from this file as text, not as binary data. Did you have a question?
I was wondering, whenever you use the / to also account for the spaces, say in the name of the folder, or...
Oh, good question. Now, I'm an old Unix guy, and I am in the habit of not including spaces in my file or directory names just to make my life easy. But if you did have a space in a directory name, so if let's suppose that my actual directory name was jostland space files, or jostland space stuff, I would have to put a / in front of the space to cause the space to be treated as a literal character part of my file name. Good question. Any other questions so far? Okay, so I just, I'm in the habit of just not including spaces in file and directory names. You'll notice that I created a directory name DFP_B3_2020 rather than DFP space B3 space 2020. Since I'm a coder, at least as much as an ordinary user, to me it always makes sense to use names that are easy to use in code. All right, and then the final argument we're going to give here is that the encoding of this file is UTF-8. It's actually an ASCII file, but UTF-8 includes ASCII as a subset, so that encoding will work fine. Now, we want to make a copy of this file, so we also have to specify an output file that should be created. We use open for creating the output file as well, and I'm just going to call this ex1 copy.py as my output file. We are writing information to this file, so instead of reading text, we're writing text. When you say WT as the type of interaction that you want with the file, that will cause the file to be created automatically by the open function. If there was already a file in the directory named ex1 underscore copy.py, that existing file would be truncated and overwritten, and you would not get any warning or error about that. So you want to choose a name that you either don't already have or that you don't care about overwriting. Okay, so that's my output file, and I'm also going to say encoding is UTF-8. Okay, so in the first open statement, I type the arguments on separate lines just to make things tidy. I also put spaces around the equal sign just because that's kind of my usual style. But you don't need to put spaces around the equal sign when you use this encoding keyword argument. So you can either put the spaces in around the equal or leave them out. Doesn't matter. Okay, good. So I've opened my input file. I have also created my output file, and I have now these objects called file handles that I can access to read data from the input file or to write data to the output file. And it turns out that a file is an iterable, just like a list is an iterable, or a string is an iterable, or the range function is an iterable. So you can read all of the lines from an input file one line at a time using a for loop. All right, so for line. Now line is a variable name that I just picked out of thin air because each one of these is going to be a line from a file. Line seemed like a good name to pick out of thin air, but I could have just as well called this ASDF. It doesn't matter. In FIN. Okay, so for ASDF in FIN, now that's going to read the first line from FIN and put that for this variable ASDF to refer to. Then, when the for loop is done the first iteration, the next line from FIN will be read, and ASDF will refer to that second line. To write this stuff out to the output file, I say fout dot write ASDF. All right. In my code in slide 64, I use this variable name line. Here I'm just using ASDF to be different. Doesn't matter. So fout is an output file object, and it understands what to do in response to this .write named method. Recall for lists we had things like append and insert and count and sort and so on. So this is a named method .write that we can use with an output file. And that's all we need to do to copy the file. We need to be careful to close that output file, because if we fail to close the output file and the program just ends, it may occur that some of the output that is supposed to have gotten written to the output file will just sort of vanish into thin air. Input and output with files is what's called buffered for efficiency. That is, when you write information into a file, usually it doesn't get written automatically. What happens instead is that your output gets buffered until you've written about 1K worth of stuff, and then that entire 1K worth of stuff gets written out altogether. fout.close will force all of the output that's been written, even if it's not a full 1K or 2K or whatever the buffer size is, to be written out into the file. Also, just for consistency, I'm going to say fn.close as well. All right, so there is my copy file program. I open the input file, I create the output file. For each line from the input file, I write that line to the output file, and then I close the output and close the input when I'm done. Let's see if this works. I save it and press F5 to run it. And it's invalid syntax because I was writing C++ code yesterday. So I don't want to use a // for a comment. I want to use a # in my Python code. Good? Okay, so we've got that syntax error fixed now. And I'll run it. And apparently it ran. Now, when I go to my let me just say file open here, and I see that yes, indeed, there is this ex1_copy file that exists, and if I open that, I see that it is an exact copy of the ex1.py file that we created last Thursday. It worked. Okay, so that's that. So we just needed to know about modules, and we also needed to know how to read from and write to files. Any questions about that? So now we're ready to go to new stuff, or now we're ready to go to the stuff that we should be talking about. We've taken a look at the list collection type. In the first part of the week 2 lecture, we're going to look at more collection types. And depending on where we are schedule-wise, we may or may not talk about type conversion back and forth among different data types. Okay, so we talked about list already. Whoops. Got my caps lock key on there. So we talked about list. Now we're going to talk about a couple of other three other collection types, namely tuple and set, and something called dictionary, which you can think of as being like a mapping data type. Frozen set is the same thing as a set, except that its items are not allowed to change. It's like a constant set that always has the same stuff in it. Once you know how to create a set, you also know how to create a frozen set, so I won't bother to talk about it separately. A tuple is apparently, at first glance, very much like a list. To define a literal tuple, you put a sequence of values between parentheses rather than between square brackets. All right, so we use square brackets to define a list, literal. Now we're going to use parentheses for a tuple, literal. And we can index the items within the tuple, either using the indices 0 through n-1 if n is the number of items, or in reverse order from -1 for the last item back down to -n, which is equivalent to 0. All right, so here I've got this little tuple called n, which contains 4 stir objects: a golden, eagle, soars. All right, so the length of n is 4. The type of n is tuple. N sub 0 is the string n sub 3 is the string soars. N sub -2 is the string eagle. Okay, n sub -1 would be soars. N sub -2 is eagle. So at this point, very much like a list, except that we use parentheses to describe it instead of square brackets. So far, so good? Now, unlike a list, a tuple is immutable. That is, you cannot modify the items in a tuple. If I try to say n sub 2, gets finch. It's not quite the correct bird name. It's goldfinch, not golden finch, but we'll take it. If I try to say n sub 2 gets finch, I get yelled at that a tuple object does not support assignment. So in this regard, a tuple is like a string. If I try to say hello sub 0 gets a capital H, similarly that's not allowed because a string is also immutable. Its elements can't be changed. All right? But although technically a tuple is immutable, it's easy to create a new tuple from the existing tuple in which you've just changed one or two or three of the items, and you can reuse the same variable name to refer to that new tuple. All right, so when I say, all right, here's n, here's my tuple. If I say n gets, and then in parentheses I say n sub 0, comma, bald, comma, n sub 2, n sub 3. Well, what I'm doing here is I'm getting the current n sub 0 item, which is Then I'm using the string bald as my sub 1 item in the new tuple. Then I'm getting eagle and soars. And after those three values, n sub 0, n sub 2, and n sub 3 have been fetched from the current tuple that n refers to, I'm just going to change the variable n to refer to this new tuple instead. And that works fine, no complaints. And now I have n referring to a tuple containing a bald eagle soars. That original tuple that n referred to, a golden eagle soars, has been reclaimed from memory so that that space can be used for other purposes. It turns out that you can take all of the items in a tuple and do what's called sequence unpacking to put those items into the corresponding number of separate variables. Or I should say, to set up the corresponding number of separate variables to refer to each of those items. So if I say, so we've seen that n has 4 items in it. If I say a comma b comma c comma d gets n, the 4 items in n are unpacked, and a now refers to the word b refers to bald, c is eagle, d is soars. Okay, so it's very convenient to take all of the items in a so-called sequence and unpack those into separate variables. The same thing can be done with a list. So if I say m gets 1 comma 3 comma 9, and I say ghi gets m, g refers to 1, h refers to 3, I refers to 9. And the same can be done with a set. So if I say q w e r t y gets hello. Now q refers to the 1 character wide string h, w to e, e to l, r to l, and so on. All right, so that's called sequence unpacking. With a tuple, you can do what's called Topopacking, which is sort of the same thing in reverse. You specify one variable name on the left side of your assignment, and then you simply give a sequence of values separated with commas, and Python assumes that you want to create a tuple containing those items. So here I'm saying t gets 1 4 high 4.6. And now t is a tuple containing 4 items. This is the first case that we've shown of a collection where the data types of the items are not the same. Okay, yesterday or last week we created a list where all of the items were integers, and earlier we created a tuple where all of the items were integers. Now here I've shown an example of a tuple where we have 2 ints, a stir, and a float. Right, so the type of t sub 0 is int, the type of T sub 2 is stir, and the type of T sub 3 is float. That's fine. You can have a mixture of types in collections like lists and tuples. So far, so good? Yes?
How would we apply the type function to every one of the tuples contents?
Excellent question. We know how to do a loop, correct? We know what the range of subscripts are within a tuple. So we could say something like this. We could say for I in range len of t. All right, len of t is 4, correct? And if I say range with 4 as an argument, that's going to give me the subscripts 0, 1, 2, 3. Up to but not including 4, correct? And now I can ask for to print the type of t sub I. Maybe I actually want to print I itself, and then the type of t sub I. Okay, so item sub 0 is an int, item sub 1 is an int, item sub 2 is a stir, item sub 3 is a float. Now, a tuple itself is a sequence, and it's iterable, so I can also say for v for value in t. Here I'm just directly accessing the items of t, one item at a time. Print v and the type of v. Good? Any other questions so far? Okay, so this is a point I wanted to get to. I'm sure we'll see an example in a minute here that you can iterate through a tuple using a for loop, just like you can iterate through a list or a stir using a for loop. Now, you can use a combination of Topopacking on the right side of the equal sign with SequenceUnpacking on the left to assign several individual values to several individual variables in a single statement. And this may just qualify as a trick. I'm not encouraging you to necessarily do this, but it works. Okay, so there I've created 4 variables, A, B, C, and D. A refers to the string high, B refers to the int 5, C refers to none. Now, notice that the shell by default won't display none when you have a variable that is referring to none. But if I say print C, then it will tell me, oh, C is referring to none, and D is referring to false. One of the places where this combination, this so-called multiple assignment, is very often used in Python is if you have 2 variables whose values you want to swap. Okay, here I have A referring to high and B referring to 5. If I say B comma A gets A comma B, well, this simply retrieves the current value that A refers to, which is high, and the current value that B refers to, which is 5. High becomes the value that B now refers to, and 5 becomes the value that A now refers to. And so I've had the effect of swapping the values of those 2 variables. That is used commonly in function definitions, where part of what you need to do is to swap values. An empty tuple is simply an empty pair of parentheses. And I didn't mention this, but that's true of a list as well. So if I say T gets open close parentheses, well, there is T, it's just empty parentheses, and the type of T is tuple, and the length of T is 0. The same thing applies for lists. open close square brackets is an empty list. And oh, by the way, the same applies for strings as well. If I say S gets 2 single quotes, well, now S is an empty string. Okay? But you run into a stupid little problem if you try to create a tuple of one item. Okay, if I say M gets square bracket 1, and I say S gets single quote Z, single quote, now M is a list, and its length is 1. S is a stir, and its length is 1. Whoops, it would be if I type correctly. But if I say T gets parenthesis 7 or 8, what is the type of T? T is an int, it's not a tuple, because the parentheses, unfortunately for us, have multiple different meanings. One meaning of parentheses is to define a tuple. But another meaning of parentheses is to simply specify the precedence and associativity for some kind of arithmetic expression. And 8 here is just the integer 8. 8 in parentheses is also just the integer 8. The parentheses there are just for, you know, forcing 8 to be evaluated all by itself as 8. So, sort of stupidly, in order to get a tuple to contain a single value, you're required to put a comma after that value before the closing parenthesis. And that will force Python to recognize, oh, this person's trying to define a one-item tuple, not a numerical value. All right, so T now is a tuple with length 1. Okay, so that's what's going on here on slide 8. You use this sort of goofy notation, parentheses containing the value, and you have to have a comma following that value in order to persuade Python, you know, hey, this is a one-item tuple, not some kind of arithmetic expression that I'm trying to evaluate. That's easy to forget, so beware of that. Good? Questions? Okay. We can do slicing on tuples because tuples are sequences just like lists and stirs. Here I've got n containing 4 items, a, bald, eagle, soars. And so I can modify n to be everything up to, whoops, colon 1. Everything up to but not including item sub 1 in n, plus the tuple harpy Now, I defined this as a one-item tuple because plus will mean to append tuples together. You're allowed to append one tuple to another tuple using plus, and you'll get a longer tuple. But if you try to append a tuple and an ordinary string, you'll get yelled at that no, you can't use plus between a tuple and a string. You can only use plus between a tuple and a tuple, or between a list and a list, or between a stir and a stir, but not between a list and a stir, or, a stir and a tuple. So I'm creating harpy as a tuple of one item. And then to that, I'm going to append n sub 2 colon, which means item sub 2 up through the end. And this notation, using slices, modifies n to refer to a harpy eagle source. Okay, I know there's lots more kinds of eagles, but golden, bald, and harpy is my range. I don't know any other ones off the top of my head. Questions? Okay, very good. Okay. All right, so we've now looked at lists and tuples. A third kind of collection that's very useful is a set. And the set in Python is very similar to the mathematical concept of a set. You can have a set of any items. The sets are not stored in any particular sorted order. You know, a given item is either a member of a set or not. There's no concept of ordering of the items. And a set in Python is not allowed to contain any duplicate values. Okay? To define a set, I can use curly braces. So here I'm saying S gets curly brace. And let me try to use, okay, 1659, 1659, 2163, 2163. Okay, so I have written down a literal set. I want to mention that in the literal set that I wrote down, 1 occurs a couple of times, 6 occurs a couple of times. That's not an error, but those duplicates will be eliminated when S gets set to refer to the resulting set. All right, so S now refers to a set of 6 items, not a set of 8 items, and the 6 items happen to be 1, 2, 3, 5, 6, 9. So far, so good. There is no concept of ordering within the set. So S sub 0 is an error. But what I can do is I can ask whether 1 is in S. And that's true. And I can ask whether 4 is in S, and that's false. I can ask how many items are in the set. Okay. A set is a collection, and I can ask what the length, that is the number of items in a collection, is. I just can't use subscripting like I can with lists or tuples or strs. There are a bunch of other named operations that I can use with set objects. I can say s.add, let's say 8, and now S contains an 8 in addition to the 6 items that it contained before. Are you noticing anything kind of suspicious here? I claimed that a set wasn't ordered. This is looking pretty ordered, isn't it? Ah, it's an illusion. It's an illusion. Don't worry about it. If I say s.pop, that will take one item randomly out of the set. Each time I say s.pop, I get one item randomly out of the set. That's looking kind of ordered too. Well, no, that's an illusion, I promise. All right, you're getting an arbitrary item out of the set. S.discard will try to discard an item from the set. If I say discard 5, that worked fine. If I say discard 14, well, 14 is not in the set, but that's okay. Discard doesn't care. We're just going to try to discard the 14. 14 isn't in there, no problem, that's fine. But if I say s.remove 14, the remove function, the remove method fails and complains if you try to remove something that doesn't exist. All right, so that's the only difference between discard and remove. Discard is always silent, doesn't ever complain. Remove will complain if you try to remove something that doesn't exist. And you can do what's called catching that error the remove function generated. I can get rid of all the items in a set by clearing it, which I won't do. And as I've already shown you, I can determine whether a particular value is in the set using the in test. Okay, so here are more examples similar to what I just showed you. Any questions about what's going on with sets? Now, all of the operations that I've done so far are operations involving a set of items and one item. All right, so when I say s.add 14, s is my existing set, and add 14 is adding an item to that set. By the way, if I try to add an item that already exists, this is also not considered an error. It's just nothing happens. Whoops. Okay, so that's fine. On slide 14, we have operations that compare two different sets to each other, or that combine two different sets together. For example, let me create an S2 here. S2 gets 4, 3, 2, 12, 11, 10. All right, so S contains 3, 6, 8, 9, 14. S2 contains 2, 3, 4, 9, 10, 11, 12. If I ask for S dot intersection S2, what I will get back is a set that is the intersection of the two sets. That is, I'll get back a set that contains the items that are both in S and also in S2. And I'm only going to get a set of 2 items in this case. There's a 9 in both sets. There's also a 3 in both sets. Anybody notice anything interesting? Oh, they're not ordered. Yay! I told you it was an illusion. Okay. Or I can ask for S dot union S2. And that will give me one set that is the union of all of the items that are either in S or in S2 or both. Now, symmetric difference is what many people call the exclusive OR. If I ask for S dot symmetric difference, and I get extra points if I spelled that right. If I ask for the symmetric difference of S and S2, basically what I'm going to get is the union minus the intersection. I'm going to get all of the items that are in one of the sets or the other set, but not both of the sets. All right, so union minus intersection. And sure enough, if we look at the union contains 9 and 3. The intersection is just 9 and 3. The symmetric difference is the same as the union with the 9 and the 3 removed. Okay. I can ask whether one set is a subset of another, or is a superset of the other, or whether two sets are disjoint. These are examples of the kinds of things you can ask about sets. Difference, by the way, let's take a look at difference. If I say S dot difference S2, what that does is to give you back S with any of the items that are in both S and S2 removed. Let's remind ourselves. Here's what S contains. Here's what S2 contains. And so if I say S dot difference S2, Well, that's basically S minus the intersection of S and S2. So it's going to be S with the 3 and the 9 eliminated. All right, so all I have left are the 6, the 8, and the 14. And the 3 and 9 are gone. And notice there's yet another example. The items are not in order. Items are not in order. Even though it looks like it a lot of the time. Good with sets so far? All right. All right, so here on slide 15 is similar examples to the ones that I've shown you. In addition to these named set versus set operations, there are also symbolic operations that you can use. And these symbols are borrowed with the same meaning from the C and C++ languages. A single ampersand is a setwise AND. That is, it's the same as intersection. A single vertical bar is the same as OR. That's the same as union. And the caret symbol, or the hat, or the circumflex, or the up arrow, that character has all kinds of names that are perfectly fine. I tend to call it the caret. Not like the vegetable. It's C-A-R-E-T. Gives you the items that are in one or in the other, but not in both. So it's the symmetric difference. And then just plain minus sign is the set difference. So here again, I have, to illustrate, I have S and I have S2. S ANDed with S2 is the intersection. S ORed with S2 is the union. S exclusive ORed with S2 is the symmetric difference. That is the union minus the intersection. And S minus S2 is the ordinary difference. That is, it's all the items that are in S but that are not in S2. Good so far? Okay. Now, there is some restriction on what you can put into a set. Specifically, the values that you're allowed to put into a set have to be what's called hashable items. And what constitute hashable items? Well, any of the scalar data types that we introduced last week are hashable. So int, float, bool, stir, and none are all hashable. A tuple is also hashable if all of the items that it contains are hashable. All right, so if you have a tuple that only contains ints, floats, bools, stirs, and or none, that is considered hashable. If you have a tuple that contains a list, however, well, a list or a set, these are not hashable. They are modifiable, and so they don't have sort of fixed, unchanging values, and so they are not considered hashable. And likewise, a tuple is not going to be hashable if it contains a list as one of its items or a set as one of its items. All right. Now there is, you know, an even more technical description of what hashable really means that would require me to talk about things we haven't seen yet. So for the moment, let's just remember, all right, any of the scalars are hashable, and tuples of scalars or tuples of scalars, all of those things are hashable. But lists are not hashable, sets are not hashable. All right, and so here we have an example of a set S3 in which we have an int, a float, a stir, the constant none, a value true, a tuple of a stir and an int and a float, false, and another int. Okay, so all of those items, the int, the float, the stir, none, true, false, another int, and the tuple containing a stir, an int, and a float, all of those things are hashable, and so it's fine for me to create a set containing all of those items. All right, but if I tried to say, okay, I have M is a list, even though M only has one item in it, if I try to say S4 gets a list containing M, I'm sorry, S4 contains an item which is a list, I get, no, a list is not hashable because a list can be changed and you're not allowed to change anything inside of a set that's already there. Good? Okay, another collection that's very important to know is something called a dictionary, or a dict, or people think of this as a map data type. Now, if we think about what we think of as an English or a human language dictionary, you have a word, and those words are ranked in some convenient order so that you can find them easily. And then associated with each of those words is a definition of what that word means. So the Python dictionary is the same kind of idea. You have a key, which is like the word in the dictionary, and then that's associated or mapped to some value. You use curly braces to define a dictionary literal, sort of like how you define a set, except that each of the items in a dictionary is a pair of values. The first value is the key, which has to be unique and hashable. All right, so keys have to be hashable. And the second item is a value associated with that key, and there's no restriction at all on the values. The values can be the same as each other. They can be different from each other. The values can be hashable. The values can be non-hashable. There's no restriction at all on what the values are. But the keys have to be hashable and also have to be unique. So the same restrictions apply to keys in dictionaries that apply to the items that are contained in a set. Here I have an example of a mapping from people's names to their current email addresses. All right, so this is the name of this dictionary I'm calling N2E. N2E for name to email. And it consists of a mapping from keys to values, in this case from username strings to their email addresses, which also happen to be strings, but that's just an artifact of this example. So if I have John as somebody's name, then perhaps this person's email is jkostland@gmail.com. Okay, so there's one item in my dictionary, and then I'm going to have Al is another item in my dictionary, and Al's email address is I can't think of an actual name. I'm going to harken back to my Swedish roots here. A. Olsen. A. Olsen at asdf.net. Okay, so there's another name and corresponding email address. And then Bob, let's say. Let me type this on the next line down. I can go ahead and just hit the enter key and keep going. We'll have Bob. And Bob is at Bob has his own company, so this is going to be Bob Associates. I'm sorry, Bob at bobassociates.com. Okay, so that's a dictionary of 3 items. All right, so the type of N to E is dict. The size of N to E, the number of items, the length, is 3. I can access individual items in the dictionary by their keys. So I use the square brackets to do a lookup in a dictionary, just like I use square brackets to do a lookup in a sequence, like a list or a tuple or a stir. But instead of using an integer subscript, 0, 1, 2 or whatever, I have to use a key value as the argument. So if I say N2E sub John, I get back the value associated with that key. If I say N2E sub Alice, I get an error because the key Alice does not exist within the dictionary. Okay? Now values, sorry, I skipped a step. We can add new items quite easily, also using the square bracket notation. So here's my N to E dictionary, as a reminder. Currently has 3 items in it. And if I say N to E sub psi colon and I mistyped that. Okay, so N to E sub psi is not going to find a key for psi, but since we're doing an assignment, what will happen is we'll go ahead and create that key, and the value associated with that is going to be Cyril at alexandria.net. So I now have 4 items in my dictionary. Does anybody know about Saint Cyril? Saint Cyril is famous for 2 things. He created the Cyrillic alphabet, and he was involved in the burning of the Library of Alexandria. So, you know, you win some, you lose some, I guess. Okay, now we can also modify the value associated with a key using assignment as well. So N to E sub John currently is my Gmail address, but I can say N to E sub John gets jostland at andrew.cmu.edu, and now that email address associated with the key John has simply been updated. Okay, so a dictionary is mutable in the sense that you can add keys, you can remove keys. I haven't shown you how to do that yet. And you can change the values associated with keys that are already there. So far, so good? Okay, so named operations for dictionary include get, which is a little less harsh than using the square brackets to do a lookup. If I say N2E sub LE, I get yelled at. But if I say N to E dot get LE, I don't get yelled at if the key doesn't exist. What happens instead is I get back a value of none. Whereas if I say N to E dot get psi, I do get back a value for psi. I can eliminate an arbitrary item using pop item, or I can eliminate a particular item by specifying a key. So if I say n to e dot pop sub Bob, pop returns to me the value associated with the key Bob and removes Bob from the dictionary. I can eliminate the entire contents of the dictionary using clear. Okie dokie. Now, collections are generally iterable. We've seen that you can iterate through a stir, you can iterate through a list, you can iterate through a tuple, you can iterate through a set. I don't think I've shown you that. And you can also iterate through a dictionary, but a dictionary is a complicated thing. A dictionary has keys and associated values, and we can think of those things together as pairs or items within the dictionary. So let me first sort of take a step back, and here's our set S2. I can say for V in S2. So V is going to take on some value from S2, one value at a time. There's no guarantee about ordering. All right, I don't know the order in which I'm going to get these things back. I sort of suspect I'm going to get them back in the order that they're displayed, but I don't know that for certain. And I can print these values. Okay, so that demonstrates that a set is iterable. And now here, I can also use a dictionary as an iterable. If I say for V in N2E, print V, this may be surprising. Because when you use a dictionary as an iterable all by itself, what you get back is just the keys from the dictionary and not the corresponding values for those keys. I get back exactly the same thing if I say for, let me use the variable name k, in n2e.keys. Okay, so the more conventional, stylistically preferred way of getting back the keys from a dictionary is to say the dictionary name dot keys, and then I can print the keys, one key at a time. Actually, I don't want these one line at a time, so let me specify my end character for each line as a space instead of a new line. All right, so there are the keys. Or I can say for V in n2e.values, print V. Now, okay, so there's a sort of an odd thing happening here, which is, oh no, wait. No. All right. I told you that the items in a set have no implied order, correct? That used to be true in Python dictionaries as well, that the keys had no defined order. But officially starting with Python 3.7, that's no longer the case. Starting with Python 3.7, keys in dictionaries are guaranteed to be stored in the order they were created. Okay, so I created John first, then Al, then Bob, but I popped Bob, and then Cy. So it's guaranteed in Python 3.7 that the keys come out in the order they were created in. So John, Al, Cy in this case. The values will come out in the same order as their associated keys. Okay, so I have John's value, that is John's email address, and then Al Olson's email address, and then St. Cyril's email address. I don't know, can we have an email address for someone who burned the Library of Alexandria? I'm not sure, but whatever. So, good with the keys and the values? You can also ask for the items. And the item each item is a key value pair. And the key value pairs are presented to you as tuples. So since there are 3 items in this dictionary, I'm going to get 3 tuples displayed here. John and John's email address is the first tuple, and then Al and Al's email address, and then Cyril and Cyril's email, or Cy and Cy's email address. So we've got three different ways of iterating through parts of a dictionary. We can go by keys, by values, or by items, key value pairs. Yes?
What does the end there signify?
What does, I'm sorry?
What does the end when you say, for example?
When I did this up here. So the print function has keyword arguments associated with it. If I just say print 1, 3, 5, 19, 22, by default, those values come out with a space in between them. But if I say print 1, 3, 5, 19, 22, and then I say sep equals comma, now the separator between the items will be a comma instead. Notice that when I got that sequence displayed, that I also got a new line so that the prompt came out on the next line down. That's called the end. I keep hitting F1 by accident. Oh, 19. It doesn't matter what these values are, I guess. So I'm going to continue with my separator equal a comma. And as my end, I can use, instead of new line, which is the default, I can use some arbitrary string. Let me use ASDF just for variety here. And what's going to come out now is 1, 3, 5, 19, 22 separated by commas, and ASDF is going to be stuck on the end. Okay, so end is how you can specify what you would like to have at the end of each output line instead of the default new line. Any other questions? Okay. All right, so here on slide 26 and 27, we have similar examples to what I've shown you. I showed you how to create empty list, tuple, list, stir, and tuple, right? For tuple, you just have the empty parentheses. And I also showed you how to create one item, stir, list, and tuple. And for tuple, remember we had that weird notation. We had to use parentheses with a comma after the value in order to persuade the Python shell that it was a tuple, not a numerical value. For creating empty and one item sets and dicts, there's also a little bit of trickery that we need to know. If I say S gets 1, 2, 3 in curly braces, what kind of thing is S? Is it a list, a tuple, a stir? It's a set, correct? Type S is set. And if I say D gets 1 curly brace, 1 colon 2, 3 colon 4, well, 3 colon 5, that works for me. What kind of thing is D? The name might give you a hint. D is a dictionary, right? They both use curly braces. And the way that you can tell literals apart is that the dictionary uses a colon, whereas the set does not. Now, what happens, though, if I say Q in caps gets empty curly braces? I've got a choice, right? And it turns out that that is how you define an empty dictionary. Okay, so empty curly braces is an empty dictionary, not an empty set. Its size is 0. So it is a dictionary, but it contains no items. It contains no key value pairs. If I want to create an empty set, what I do is I say a constructor function name set with parentheses. Okay, now S is a set, and the number of items in S, capital S here, is 0. And so that is the annoying difference in creating an empty dictionary versus an empty set. And I promise you that you will forget this, and you will try to create empty sets using empty curly braces, and it will not work, and you'll be frustrated. Okay, so remember that empty curly braces creates an empty dictionary. The construction function name set with empty parentheses is how you create an empty set. Now, given Q, which is empty, I can say Q sub, what am I up to? F phi. Q sub phi gets Fiona at asdf.org. Now Q has one item in it, and given my empty set, I can say s.add, and now S has one item in it. Okay, so that's a nuisance to remember, just like you have to remember the comma thing when you're creating a one-item tuple. Yes?
I was wondering, is there a function like there is a set to define a dictionary?
Yeah. Okay, so in fact, you can create an empty stir by just using the string construction function with empty parentheses. So that's an empty stir. This is an empty list using list construction. This is an empty tuple. This is an empty set. And this is an empty dictionary. So you can use these construction function names for each of these collection types to create an empty one by just leaving the parentheses empty. Okay? Slide 29 shows how to create one-item dictionaries and sets. And it's important to realize that because of the lack of ordering of sets and the key ordering, the key creation ordering of dictionaries, these things are not sequences, and therefore you can't do any slicing. If you try to use slicing on either a set or a dictionary, you'll just get yelled at. All right, well, on Thursday we will pick up looking at conversions, so I'll see you then.
Professor Osborne.